Let's now turn to a numerical solution for parabolic problem. The first method we are going to show you is the so-called explicit method. We recall that parabolic equation takes the following form: the usual parabolic equation called the heat equation, and the spatial coordinate x is between 0 and capital L. The solution is of course a function of the spatial coordinate x and the time t. And we recall that this equation for c equal to 1 takes the following form. We have an initial condition which should be satisfied. That is the condition for t equal to 0. Then we know the temperature in all points. Moreover, we have that the boundary values are satisfied, and usually we write that the boundary values are equal to 0, just for simplicity. Recall now that we have the following approximation for the discretization of uxx. This is the same as we have done before by using Taylor expansion. And we note here that we have discretization in the x variable, so h is the step length in x direction. It is the value, the length of each of these small rectangles in the x direction. Moreover, we have a step length k in the t direction. Usually for the harmonic problem, when we have Laplace equation, then we use the same step length in both the x direction and, in that case, the y direction. In this case, we usually must have different step lengths. And we remember that the derivative of u with respect to some variable t, actually we prove this for the y in the y direction, but it's exactly the same when we replace y by t. So therefore we have this expression for this derivative, the partial derivative with respect to the time t. And we these values are in the point ij. I'm sorry that I often say g, but I mean j. Okay, so in the parabolic equation, the heat equation, we should put this this expression equal to this expression. So let us just do that. For simplicity, we assume, as I've told you, that that c in the heat equation is equal to 0. And then we get this equation. So here is the left side of the equation on the discretization form, and here is the right side of the parabolic equation. If I now multiply each side of this equation with k, then you see here we get k over h square. And this is an important parameter. Then we can write this discretization equation on this form. So by using this discretization equation, we get a method for solving the parabolic equation which is rather trivial. It's called the explicit method. And let's just show how this is done. It's very simple to do this. We note here that we have this way of discretizing the problem, h in this direction and k in this direction. So let me just show you. If we, for example, want to find the value in this point, the equation, discretization equation, which we found now, show that this value is obtained by finding the value in this point, or using the value in this point, and in this point, and in this point, together with the value of r here, which we have to assume that we have put some value on this initially. So, for example, if we are going to compute the value of the temperature in this point, we use these 3 points as basis, and by the discretization equation we find this value. If I want to find the value at this point, we just use these 3 points and use the discretization equation and find the value in this point. If I want to go to find the value in this point, I can use these 3 values. Note that this value is, we know this value because of the boundary conditions. Recall that the boundary conditions are 0. And we now have computed the values in these 2 points, so therefore we can find the value in this point by using the discretization equation. So working with these initial conditions and the discretization equation, we are able to find all values in each point. So the only thing that we have to be aware of is that this parameter r, which is k over cap h square, has to be less or equal to 1/2. This is possible to prove by using some more advanced mathematical methods, but this is a rather important condition in order to get convergence. That means that when, of course, we want the situation, we want that when h is converging to 0, that the step length in this direction and step length in the time direction is going to 0. We want that the numerical solution should converge to the actual solution. And this will happen, but only if k over h square is less than 1/2. So this is important for the explicit method. There is so this is the disadvantage of the method, that we have to make sure that this condition is satisfied. Another obstacle is that the explicit method is has slower convergence than the method that we are going to show you very soon, called Crank-Nicolson's method.